Okay, so I wanted to make videos of using Gauss's law for two cases that we may not have done in class. The two classes actually ended up differently, so this might be a review for you or it might be totally new. So the two examples we're going to look at is the electric field due to a line of charge and then the electric field due to a sheet of charge. So we start off with Gauss's law. And our goal is to, this integral is assuming that we enclose our charge distribution by a surface, which we call the Gaussian surface. And we're trying to choose something that mimics the geometry of the charge that we're looking at that's causing the electric field. So in this case, we have just a line of charge. And so its charge is, we might call it charge density, but it's a charge per unit length. We use the letter lambda, and it represents Q divided by L. So it would be something like microcoulombs per meter or something of that nature. We are going to assume that our line of charge is infinitely long because when you cut it at the ends, the electric fields get wonky. Now, we might be able to assume, or maybe not, that what's going to happen is this line of charge is creating an electric field that radiates outwards away from the line of charge. And this is important also for choosing our surface. And what we do is we choose a cylinder as our surface because it mimics the shape of a line of charge. You know, a line of charge is just a super skinny cylinder, and what's going to happen is we're going to have on the sides, we're going to find that the electric field and the area vector are going to be parallel to each other, so that will contribute to the left-hand side of Gauss's law. But here on the endpoints, if we look at dA, we'll see that the electric field is perpendicular to the vector dA, and so E dot dA at the ends is 0. And so the top and bottom of the cylinder are not going to contribute to our integral. So I like to split this up into two pieces. The top and bottom, and E dot dA for the sides. Now, because of the fact that E dot dA, the electric field, which is these red vectors here, and then the dA, the area vector, is this blue right here, because they're perpendicular to each other, this integral makes no contribution. Now, for the sides, we have E dot dA, but because they're parallel, we can just write it as EDA, and because the electric field is going to be constant, because the sides will be a constant distance from the line of charge, we can take the E out of the integral, and we get just E times A. Now, how do we find the area? The area is going to be the circumference of the circle that is at the top of the cylinder, and then times its height, which is L. So that would be the area. So E dot dA simplified to E times A, which is going to be E times 2 pi RL. Now we want to set that equal to the charge enclosed over epsilon naught. If my cylinder has a length of L, because lambda is Q over L, if I make this Q the enclosed and I multiply and I say this is the length, the Q enclosed is going to be lambda times L. So I'm going to make this lambda times L over epsilon naught. So let's kind of see what's the equation I'm at right now. So I want to solve for E. And I'm going to group things a little bit differently now. I got 1 over 2 pi epsilon naught times lambda L over R. This is actually equal to twice K because instead of 1 over 4 pi epsilon naught, it's equal to 1 over 2 pi, so it's twice as big. And so my final answer for my electric field due to a line of charge at some distance r away from the line of charge can be expressed like this. 2 times the Coulomb constant times the charge per unit length, which is lambda, over r. So what we see here is the line of charge only falls off as 1 over r, where a sphere of charge fell off as 1 over r squared. Just a little difference to notice. Okay. So we did that. Now, the other thing that we wanted to look at is a sheet of charge. In this case, we're spreading the charge over an area, so we use this letter sigma, which represents charge per unit area. Now, one of the things that we want to see is like, well, what is the direction of the electric field in this situation? It actually is perpendicular to the sheet of charge, because if we took two pieces of charge sort of equidistant from some central point and looked at the electric field, we can see that their x components or their components parallel to the sheet will cancel out, because we have this and we have this, they cancel out, but the y components or the perpendicular components will add up. So we kind of go in knowing that the E is perpendicular to the sheet. And what we're going to do is, in this case, we're going to take a cube shape for our Gaussian surface, because for our cube, and I'm just going to rewrite Gauss's law down again, because that's always going to be where we start. For our cube, we'll sort of have, we'll do E dot dA, and from this picture we have side 1 and side 2. So those are the two sides that we would do. And then the other ones would be the E dot dA, which would be all four sides that are perpendicular to the sheet. This is going to be similar to the cylinder in that some of the pieces of my Gaussian surface are not going to contribute at all, and some will. And that's why I split it up into these two pieces. The side 1 and side 2, which to me really are more like top and bottom, are the ones where my electric field and my area vectors are going to be parallel to each other. But all the other four sides, here, 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 and back here, you can see that the electric field and the area vectors are perpendicular to each other, so those will not contribute. So I'm left with E dot dA for side 1 and 2 equals Q enclosed over epsilon naught. This turns into E times A, and E can come out front, times dA. dA. And actually, because I do side 1 and side 2, even though if both of those have an area of A, my total contribution when I integrate dA is 2A, because I have 1A each for side 1, side 2. That's why I have 2A. And this is equal to the charge enclosed over epsilon naught. Now, finding the charge enclosed has to do with the definition of the charge surface density, which is sigma, which is charge over area. So my charge that I enclose in my Gaussian surface will just be given by sigma times that area. So I have 2EA is equal to sigma A over epsilon naught. And if I solve for E, I get sigma A over 2A epsilon naught. So I'm left with sigma over 2 epsilon naught. And that becomes the expression for when I have a thin sheet of uniform positive surface charge density sigma, I will find that its electric field is going to be perpendicular to the sheet itself, and its strength will be determined by the surface charge density over 2 times epsilon naught. Okay, so there were some time to go through some questions, so let's just go over those. So we have a long wire. And we're looking for the electric field some distance away from it. And let's just remind ourselves of the expression that we found for the electric field due to a long, thin wire at some distance r away from it. And we're saying, oh, well, at one distance, its strength is 1,000 newtons per coulomb, but where would we have to go to get it twice as strong? So to get the E to go from 1,000 to 2,000, we know that R has to get smaller. And because E is proportional to 1 over R, we can just get that factor. We want it 2 times bigger, so R should go to R over 2. So we want it to be half as big, because if we go half as big, closer, will make it E stronger. Now in this particular question, they replaced R with D, and so instead of choosing R over 2, I will choose D over 2. Now, this question has to do with 2 long infinite wires that have a particular charge per unit length of density. I'll call this one 1 and this one 2. And what we're told is lambda 2 is equal to 2 lambda 1. So this is lambda 1. That's the charge per unit length of wire number 1. Wire number 2 has twice that charge per unit length. Keeping in mind the electric field due to a long wire is 2k lambda over R, I can see that the wire that has the higher lambda is going to have a stronger field. If we look in between the 2 wires, this would be the direction of E1. That would be the electric field between the wires caused by lambda 1 or wire 1. The direction of the electric field by wire 2 is going to be in the opposite direction. So they can cancel out, but remember, I want their magnitudes to be equal to each other. And so because E2 has the higher lambda, we need to go closer to number 1. And so they're going to be cancel out at some line that's right between them, but it has to be closer to number 1 than number 2. And then finally, we have a chance to do some calculations just to practice it. We have the electric field due to a long wire, so we know lambda is -3 times 10 to the -9 coulombs per meter. The electric field 30 centimeters away. Well, we do E is equal to 2k lambda over r, so 2 times 9 times 10 to the 9th times lambda is -3 times 10 to the -9, and then over 0.3. And that negative sign means that it's going to point towards the line of charge. The second question has a spherical insulator that has 5 nanocoulombs distributed uniformly throughout its volume, which is a radius of 50 centimeters. So Q total is equal to 5 times 10 to the -9 coulombs. We're going to be asked, we're finding the field inside and outside, because when we're asked for the radius of, to find it at 25 centimeters, we'll actually be within the sphere, and when we're finding it at 75, we're outside. I'm going to do the electric field outside first because it's easier, because what we found is once we get outside of an insulator sphere, even though it has a certain size to it, it ends up looking like the electric field at a point charge that was placed at the very center of the sphere. So this is 9 times 10 to the 9th times 5 times 10 to the -9, and then 0.75 squared. And this is equal to 80 newtons per coulomb. I'm going to do the inside on the next page because I don't have any room. Our expression for the electric field inside is a little more complicated. If we remember, we got an expression that depended on R, because what happens is that as you get further from the center of your sphere, you have enclosed more and more of the charge, and so the electric field grows, and so that's why that has that dependence of R. So we're going to do 9 times 10 to the 9th. The total charge was 5 nanocoulombs. We're looking at 25 centimeters, and then the total size of the radius is 0.5 cubed. And I got 90 newtons per coulomb. Now, I want to warn you that these problems, I sort of made them so that you could just put your numbers into the expressions, but in the assessments, these types of questions will say, use Gauss's law. So you will need to go through the steps that we did in class in order to, in class or on the video, in order to come up with those expressions and then find the values. You will not get credit if you just write down the expression and plug in the numbers. So just a little warning, maybe take a look at the example LOs for reference.